Okay, hi. This lecture should be a self-contained lecture on the method of moments for finding estimators. So again, if you reflect on what we've been doing, we haven't really talked about general methods for finding estimators. We've sort of given these intuitive estimators like the sample mean for the actual mean for mu, say, of a normal distribution. But we haven't talked about methods, general methods for finding estimators for unknown parameters. So we assume we have a sample from a known distribution, but one or more of the parameters are unknown, and we would like to define methods for which we can find those parameters. So the first one is called the method of moments. So let's see. So method of moments. And this is a pretty simple idea. We assume we have a sample yi I equals 1 to n iid comes from a known distribution with one or more unknown parameters. And okay, so we have some definitions. We'll define, just for convenience, mu k prime equal to expected value of yi to the kth power. So this is called the kth central moment. And we'll define mk prime equal to 1 over n sum yi to the k, and this is the kth central or sample central moment. So here we want to put the word sample. Kth sample central moment. So when k is 1, this is just the sample mean, which is an estimator for expected value of yi. So the method of moments then. So suppose if we want to find estimators for t unknown params, we solve mu k prime equals mk prime for k equals 1 to t. Okay, yes, so this should make sense. The parameters appear here, right, in this expression, in the mu k side, on the left side. On the right side, I have numerical values from my sample, right? So if I have t unknown, I have to solve, I typically need t equations to solve for the parameter. Okay, let's do an example. So for example, suppose yi is uniform 0 theta for I equal 1 to n iid, and we'll say estimate theta by method of moments. Okay, so in this case, we just have t as 1. There's just one equation and one unknown. So mu 1 prime equal e yi is equal to theta over 2, expected value of any yi, and m1 prime is just equal to 1 over n sum yi. This is, you can always write this like y bar. Okay, so this maybe should be a big y bar, but when you're solving it, or this should be a little y, but the idea is once you make the estimate, you're using actual observed values. So solving this, so we have theta hat, method of moments is equal to 2 y bar, which should make sense, right? If I sample many times, I expect y bar to be near theta over 2, near the middle. And so if I double it, I should get something near theta. Okay, to give a little more detail to this discussion, I'll just define a new attribute that an estimator can have. So we'll make this definition. An estimator, any estimator, theta hat. This is not just for method of moments, is called consistent if limit n to infinity theta hat n, if the variance of the estimator as n goes to infinity is equal to 0. And here theta hat n refers to, means the sample size. So it's the same n, is n, just to be clear though. So if the variance of the estimator goes to 0 as I take more and more samples, this implies that the estimator is going to a constant. So I'll always get the same estimate for the parameter if I take a lot of samples. I'll get something near the same number. Okay, so to see an example, let's look at the above for the above example. For example, above, we see the method of moments estimator is consistent, and this is good because we have variance of theta hat n is equal to variance of 2y bar. So this is equal to, the 2 comes out as a 4, the 1 over n comes out as a 1 over n squared, so I get 4 over n squared, sum variance of yi, and the variance of a uniform 0 theta random variable is theta squared over 12, so I have 4 over n squared, and I have n theta squared over 12, which is equal to, let's see, theta squared over 3n, and that goes to 0 as n goes to infinity. Okay? So I just wanted to give this definition while we're here. All right, let's maybe do one more example, and then this will end the lecture. It's a simple and old method for finding estimators. So let's just do one more maybe. So suppose, example 2, then I'm out of time. So suppose let yi be normal, and suppose both mu and sigma squared are unknown. Okay, what is the method of moments estimators for mu and sigma squared? Then we have yi is certainly equal to mu, and yi squared, this is equal to variance of yi plus EYI all squared, right? If I manipulate that equation for variance. And so I get this is equal to sigma squared plus mu squared, right? That's the second central moment. And so we need to solve, so solve mu equals y bar. That's the first equation. Sigma doesn't appear in there. And then the second would be sigma squared plus mu squared equals 1 over n sum yi squared. I can do this. I already found mu, so I will substitute in here. So this gives sigma squared equals 1 over n sum yi squared minus y bar squared. Right, minus y bar squared. Okay. Okay, that's it. Let's see. I'm just trying to think if I could write this any. I think that's clear enough. I'm almost out of time too. So this is the method of moment method for finding estimators.